Example, use the graph of y equals f of x and the sign chart for f prime of x to answer the questions that follow. A. Is the function concave up or concave down? The graph shows an open or upward facing parabola, so we say that this is concave up. Is there a minimum value or a maximum value at x equals c? Well, we notice that while it is concave up, that would mean that the second derivative is positive. The extreme value that we see is a minimum. So the extreme value for the second derivative that's positive is a minimum. Example, use the graph of y equals f of x and the sign chart for f prime of x to answer the questions that follow. A. Is the function concave up or concave down? The graph given is an upside down parabola, so we call that concave down. Question B. Is there a minimum value or a maximum value at x equals c? Let's observe and remind ourselves that when it is concave down, the second derivative is negative, and the most extreme value that's located on this graph is a maximum, so we have a maximum. So negative second derivative, the extreme value is a maximum. The second derivative test for relative extrema. Suppose f is differentiable for every x in an open interval a to b, and that there is a critical value c in that open interval ab for which the first derivative evaluated at c equals 0. Then 1. F of c is a relative minimum if f double prime of c is positive. And 2. F of c is a relative maximum if double prime of c is negative. For f double prime of c equal to 0, use the first derivative test to determine extrema. Example, use the second derivative test to find local extrema for g of x equals x cubed minus 9x squared plus 24x minus 10. To find relative or local extrema, we need critical values. So let's first find critical values. Critical values are where the first derivative equals 0 or is undefined. Since g of x is a polynomial, it is everywhere defined. Let's proceed to find the first derivative. That would be bring the 3 down, then you have x 1 power less is squared, minus bring the 2 down, that'll be 18x, plus 24. Critical values, again, we need to set this equal to 0. So 0 is equal to, I'm going to factor out a 3, and you get x squared minus 6x plus 8. Continuing to factor, I could do x minus 2, x minus 4, setting each of the two factors with variables equal to 0. X minus 2 equals 0, x minus 4 equals 0. I get a critical value at x equals 2, and another critical value at x equals 1. We've got critical values. Now we need to see if they are local extrema. We do that by finding the second derivative. So g double prime of x is the derivative of the first derivative, so we would get 6x minus 18. Now let's evaluate. At x equals 2, g double prime at 2 is equal to 6 times 2 minus 18. 12 minus 18 is a negative number, and a negative number is less than 0. If the second derivative is negative, then it is concave down, and so the most extreme point is a maximum. You have a relative max at 2 g of 2. Let's do this for 4. Got 6 times 4 minus 18. 24 minus 18 is a positive number. That's greater than 0. If the second derivative is positive, the graph opens upward, and the most extreme point is a relative minimum. Therefore, we have a relative minimum at the ordered pair 4, G of 4. Healthy Endeavors estimates that it will sell N of X units of a newly developed heart function monitor after spending X $1,000 on marketing, as given by N of X equals negative 0.25x to the fourth plus 23x cubed minus 360x squared plus 45,000 for X between 25 and 54. What is the rate of change of sales increasing and decreasing? And what is the point of diminishing returns and the maximum rate of change of sales? Before we continue, we need to know what the point of diminishing returns is. If a company decides to increase spending on marketing, it would expect sales to increase. At first, sales will increase at an increasing rate and then increase at a decreasing rate. The dollar amount X at which the rate of change of sales goes from increasing to decreasing is called the point of diminishing returns. Computationally, the point of diminishing returns is where concavity changes from concave up to concave down. So to solve this problem, we need to get to the second derivative. Let's begin. First derivative. Bring the 4 down, so we'll have negative 1x cubed plus, bring the 3 down, 3 times 23 would be 69x squared, minus, bring the 2 down, that would be 720x, and the derivative of 45,000 is 0. Let's continue. The second derivative, we bring the 3 down, so we'll have negative 3x squared plus, bring the 2 down, so that will be 2 times 69 or 138x minus 720. What we need now is to see where concavity changes, so that's where the second derivative equals 0. 0 is equal to, I'm going to factor out a negative 3, then I would get x squared minus 46x plus 240. Now let's continue to factor some more. 0 is equal to negative 3. We're going to have 2x minuses. And what factors of 240 will give us a sum or difference of 46? And I believe that'll be minus 40 and plus 6. So the numbers that we get are x equals 6 and x equals 40. Now we need a sign, chart, number line for the second derivative. And this gets interesting because one of the numbers is 6. When x is 6, the second derivative is 0. And when x is 40, the second derivative is 0. However, we have a domain restriction. That domain restriction says we can only consider values between 25 and 54, so we don't have to pay attention to the values that are not in the interval between 25 and 54. Now we'll select a value between 25 and 40 and evaluate it in the second derivative. I'm going to pick 30. Put 30 in the second derivative, so 30 minus 40 is negative. 30 minus 60 is positive. So I've got negative, negative, and positive. That gives us a product of positive. Now let's pick a number to the right of 40. 50 is an easy number to pick. So we'll have negative 3 times 50 minus 40 is positive. 50 minus 60 is positive. So 1 negative and 2 positives. The product is negative. So we have concave up from 25 to 40 on our domain and concave down from 40 to 54. The point of diminishing returns is the ordered pair 40 and the function evaluated at 40. The instructions stated to find the maximum rate of change, and to do so, compute n of 40 on your own. When you do, you should get the number 301,000. You put 40 into the original function.